Hello, my name is Adora Guice. I am from Jackson, Mississippi. I attend Mississippi State University. I am a rising senior, major in computer science. I had the honor to come to the University of Florida for their SURF program of 2022 to work with the material science department. Since I am working on a computer science degree, I decided to work with Dr. Tonks and Vishal on the comparison of different grain growth models. To begin this research, we started by comparing the Monte Carlo plots and phase field, which are two different simulations that are used for grain growth. The process for this research included using the Atom and Moose program. We had to use the input file to change code, then upload to the terminal to run these simulations. To start things off, we used circular grains for phase field and Monte Carlo plots in 2D. The formula at the top is the way we calculated the area. The phase field model connects with the analytical solution in 2D quite well. With the Monte Carlo plots, using the same function of area, we compare zoner graph shown in the left to our graph. The matches quite well. It varies a bit because of the points that were chosen. This right here shows the surface area function that we use for phase field and Monte Carlo plots in 3D. The phase field model matches accurately until the time goes up. This Monte Carlo plots in 3D did not match the donor graph in the left like we expected with KT parameters equal to 0 through 3. Since we did not get the results we were expecting for Monte Carlo plots in 3D, we changed the neighboring site from 8 to 4 in 2D to make sure everything was right on our part. After comparing the two models, we went into comparing standard and pseudo-sign distant function, also known as PSDF, with phase field model. The function above shows how the standard was changed into the PSDF model. The purpose of this is that standard phase field model requires a lot of computational resources. The PSDF phase field model was proposed in 2001, and it claimed that it requires less computational resources, which were not studied properly. Both these models show element 1 through 6, comparing them with the analytical solution. In the graphs, if you give them a close look, the PSDF phase field model has more elements aligned than the standard phase field model. The graph here is comparing element 6 standard, which was the best of all the standards, to the PSDF elements. We found that at least 3 elements in PSDF is better than element 6 standard. This right here is the comparison of standard phase field and PSDF phase field model, and it shows that the PSDF is way much faster than the standard phase field model. When finding this out, we wanted to know how does the tolerance impact the PSDF results. So this led us to using element 3 and 6 with the tolerance study. The results of changing the tolerance were similar between the two elements. Through this research, we found if someone was to change the tolerance level, then 5, 6, and 7 were better than 1 through 4 tolerance level. In conclusion, relative error in PSDF model with 3 elements is less than standard model with 6 elements across interface. The time step for PSDF is 10 times larger than standard. Also, computational resources requirement is less for PSDF model. And then, if impact and tolerance level 5 or greater is the better results. I would like to give thanks to Dr. Michael Tonks and Vishal for letting me be a part of this research and helping me through it. I would also like to give thanks to Mike and the University of Florida for the SURF opportunity. This includes the research trips and many connections made through the summer.